Hello, everybody. James here. Welcome back to another episode of the Flocode podcast. Happy New Year to everybody. 2025, maybe the final year of UFO disclosure. We don't know. Today, we're joined by Dr. Morten Engen, civil engineer at Multiconsult and an adjunct professor at the Norwegian University of Science and Technology. He is the lead developer of Structuralcodes, which is what we're going to talk about today. That is an open source Python library for structural engineers, a remarkable tool. So I'm looking forward to digging into that. And Morten, why don't you give us a little bit of background, who you are, where you're from, and then we'll jump into Structuralcodes.
Yeah, sure. I'm Morten. I'm from Norway, and a little town outside of Oslo, the capital of Norway. I live at Fornebu, which is also just outside of Oslo, where I live with my wife and my two kids. I've studied civil engineering in Trondheim, where I graduated with a master's degree in 2012. Since then, I've been at Multiconsult in Oslo, one of the biggest consultancy offices in Norway. And I did my PhD from 2013 to 2017. And from 2018, I've had a position at NTNU where I'm lecturing and supervising students, etc.
Awesome.
Yeah.
And so to give people a flavor of the type of industry and the type of work that you've done, what kind of sectors have you worked in?
Oh, good question. Well, I've been working mainly inside energy and industry, so that's kind of where I live in the company. But I'm assisting projects quite widely. So we're building a subway to or from the city center and out to Fornebu. That's a project that I'm supporting, and various other projects like that. So
So a
typically,
wide variety of stuff.
yeah, more or
Cool.
less.
Yeah, similar to me. I'm predominantly in energy and water. Okay, so this is going to be an interesting episode because we're going to show structural codes. We're going to show some of the architecture and how it all works. So Morten's going to share his screen along the way. So I ask people that are tuned into this that if you're watching this on your phone, no problemo. However, just be aware that sometimes trying to understand code on your phone is a challenge, to say the least. So if there's something that we go through that you're not sure of, just get to a desktop and go back and check out that particular part of the episode. So first up, I guess, Morten, what is structural codes? What is it?
I think you really got it in the introduction because it's an open source Python library, and it's a library for structural engineering calculations. And I mean, our scope is to provide Python implementations of the most relevant parts of our design codes in order to provide building blocks for engineering workflows. So until now, we've kind of been focusing on reinforced concrete and the material from Eurocode 2 and the FIB model code. FIB, that's the International Concrete Association, and the model code, that's the reference code of the FIB. However, the structure is designed in such a way that we should be flexible enough to handle also other codes and materials. And I mean,
Yes.
it's also perhaps worth to note that it's a kind of a backend library. So meaning that we're developing functions and classes that can be used to build scripts, notebooks, or web or desktop applications. So we're not kind of developing graphical user interfaces or plotting tools, but we're encouraging building tools on top of structural codes that can do this.
So I think it's very important to distinguish the difference, the specific niche that structural code serves here, because on one hand, you've got many different types of structural analysis tools where you've got frame analyzers, or you figure out reactions of a certain structural system, or you're figuring out the stresses in the corner of a steel plate, etc. You're analyzing your structure, but structural codes doesn't do that part. That kind of steps in after you've understand your analysis, you understand your results, and then it's the process of, okay, I understand the demands on my structure. Now I need to figure out how these demands fit in with whatever local regulatory code that you're working with. In your case, it's Eurocode.
Exactly. Yeah. So
So,
it will be more related to the capacities and less related to the demands then.
and I had this conversation before with somebody where I had said, why are there no capacity based tools? And there are commercial tools available, but why are there no open source capacity tools? And he said, because it's impossible to maintain, it's impossible to keep up with changes in interpretation and in the actual code itself. And I think it is possible. Like you're already doing it for Eurocode. So tell me, like, where did this idea come from?
Yeah, that's a good question also. I mean, it's a good comment to spin that out from. In 2022, I gave a keynote speech at the FIB symposium in Oslo, Norway. And I had kind of the same backdrop as you were describing there. And in the talk, I was proposing a couple of challenges to the FIB. So one was related to their research databases, and the other was to actually to take the initiative to create the Python library with design equations from the FIB mold code. So my idea was that the FIB could or should take lead in such work in order to make sure that the library should become top quality and open source. And in that way, the industry could take ownership of it and everyone could contribute to developing and maintaining the bread and butter of our engineering design workflows.
Mm-hmm.
So a couple of hours later, I was kind of challenged back. And later the same year, the task group that we formed was put together.
So so by the process of giving that presentation with your ideas, you volunteered yourself to
Well,
spearhead this initiative.
I kind of did not volunteer, but I could not say no.
Yeah,
Mm.
you were selected. Okay, and so you mentioned the FIB's involvement. Have they been, has been their level of support, or what has been their level of guidance? Have they just kind of said, Morten, go onto your computer and come back when you're ready? Or has there been discussions of how this should be structured, etc.?
Yeah, I mean the role of the FIB is perhaps both formal and informal. So after my keynote in 2022, I was quickly approached by Professor Alejandro Perez Caldente, an active FIB member in various groups, and who I knew from various situations from before. He immediately supported the idea, and in the evening when I entered the dinner hall, I met Professor Aurelio Muttoni, and he stopped me in the door and simply said, "I think we need to talk." And well, after the dinner, Professor Muttoni asked if I had already spoken to David. And then I was a bit confused because I was unsure which David he was referring to. But then quickly realizing that this was actually David Fernandez Ordonez, the Secretary General of the FIB. So after a quick chat with David on the way out, he was already starting to planning our first task group meeting. And before that meeting, he had already spoken to several interested contributors, including Professor Caldente and his team from Flocode in Madrid, including Arthur and Gijs from TNO in the Netherlands, and Diego Alejandro Toledo from the University of Venezia, who is the co-convener of the task group. So, I mean, my point of sharing this is to say that the FIB provides the network, and without the careful nudging from David, Secretary General, I would not have met with Diego, and without Diego, we could not have delivered the high standards that we have today. So the two of us meet quite often online. We chat almost daily on WhatsApp, and he's become not just the co-convener of the task group or the co-maintainer of the library, but also a really good friend of mine.
That's awesome,
Yeah.
and a fantastic testament to how things are changing now, and even just this platform, the ability to talk with you about this and to share this with other engineers, to help them in their own work. It's remarkable, and I feel like the last couple of years there's been a big shift in the perception of programming and how useful it is for engineers. A lot of younger engineers now are starting to show a lot more interest,
Hmm.
and I do wish that more university programs did provide a bit more comprehensive instruction on how to program. But I think we're getting there slowly.
Yeah.
Um, okay, cool. Well, thanks for the background. Let's jump into it. Like, let's get your screen share going,
Yeah.
and let's explain to people. So, structural codes for everybody. It's available on GitHub, and we'll share all of the relevant links in the description below. And Morten's just going to share his screen here, and we're going to go from the absolute basics through what this library is, how it works, what it does, etc. So I'll jump in here and there, Morten, with some questions for you. So please just take
Sure.
it away as you see fit.
All right. So on my screen now, you see the landing page in our online documentation. We will share a link to this as just mentioned. In the documentation here, you will see how to install the library. So it's pip installable like a regular Python library. You will find a quick start example, and you will find API reference, and you'll find a contribution guideline. I intentionally now skipped examples and theory reference because these are sections that we are working on. These are not really
They're the
filled
first
yet.
two sections that my eyeballs are magnetized to. As soon as I see the list, it's like that's where I want to go immediately.
Exactly. Yeah. So hopefully we'll get some good material in there
Okay.
soon. But I mean, the quick start is a good place to start. Obviously, the API reference is complete. So if you wonder whether something is covered by the library, you can browse that also. If we head over to the quick start, I figured I can scroll through this one. I will explain the steps of it, and then we can switch to Visual Studio Code and we can try experimenting a bit with
Awesome.
the code as well. So in the quick start, we will see how we can use structural codes and Eurocode 2, which is the governing design code in Europe, to model a rectangular reinforced cross-section and do some calculations on it. So first, in this first block here, we import Shapely, which is a library for drawing geometries, and we import various parts from the structural codes library. In the next block, we set the active design code. This is a factory function, or not just a factory function, but it kind of sets a global pointer to the active design code in the library. So here we set it to Eurocode 2. Now in the next block here, we define some parameters. So material parameters, the strength of the concrete, the yield strength and the ultimate strength of the reinforcement, Young's modulus of the reinforcement, and the ultimate strain of the
So I'll
reinforcement.
just quickly jump in here, Morten. For anybody that's
Sure.
unfamiliar with the Eurocode, all international code standards have the same properties, just with slightly different variable names. So if you're using any other
Mm.
tools out there, you first of all need to just define a specific design code, as Morten mentioned, like Eurocode 2, and then we assign these variables throughout. Okay, carry on, Morten.
Mm. Yeah, thank you. That's a good point. Next, we're using factory functions to create materials. So here we create a concrete material and a reinforcement material. These two objects, they are objects of type material. So, I mean, they are objects that store properties, so material properties, and they also store pointers to constitutive laws that we can use in say an iterative solver in order to trace a stress strain
So
diagram, for
what do you
example.
mean by constitutive laws?
So that would be a relation between stresses and strains for a material. So for example, a linear elastic one, or a parabola rectangular one, or a elastic plastic one,
So
for
everything
example.
tied to stress, strains, or deformation of a cross section.
Yeah, you got it. In the next block, we create geometry objects. In structural codes, the geometry objects, they contain both a polygon and the material that's related to this polygon, or a point and the material related to the point. So we define a width, a height, and we construct a polygon. So this will be our rectangle for the
Mm-hmm.
rectangular cross section. And we're creating a surface geometry. So here you see that we refer to the concrete object again. So geometry here, that's the polygon with some material assigned to it. In the next block, in this one, we add reinforcement to the geometry. So we define reinforcement with diameter 25 millimeters and a cover of 50 millimeters. So these two function calls, so the function call to add reinforcement, basically takes the geometry, adds a point to a given coordinate, and this point is assigned the reinforcement material, as you see here. And we do it twice, so we have 2 bars in our cross section. So now the geometry is no longer a surface geometry, but it's a compound geometry. It's a compound of a
Mm-hmm.
surface and 2 points. And kind of the final step to prepare for our calculations, we create a section object. So the generic section class, or you can think of the generic section as a calculation tool. So something that wraps the geometry, the material, and adds methods or attributes to it so that um, we can integrate strain response
Mm-hmm.
over the cross section and with different method calls for doing different types of calculations. So in this block at the bottom here, we call what we call a section calculator to calculate the moment curvature relation. When we switch to Visual Studio Code now, I will demonstrate what this
So
does.
we've defined the perimeter of the cross section, which is a rectangular cross section. We've defined two points which
Yeah,
represent our reinforcement, and then this final generic section function that literally creates that 2D full section and combines everything
exactly.
together.
Yeah,
Gotcha.
it does. Yeah. So the geometry is already ready from this stage, but then we wrap it with some methods
Gotcha.
to work on it as well.
Cool. That's awesome.
Right. Let me share my Visual Studio Code window as well, and we can start exploring this a bit more. And please feel free to interrupt along the way if there's anything which is unclear.
So I guess before we jump into the actual code here, are there
Yeah.
any specific extensions that you like to use, or what way do you suggest people work with structural codes? I use Jupyter notebooks
Mm,
personally in VS Code, just like what you're doing right here. This is
yeah.
how I typically do it, and I'm guessing that's what you would probably recommend.
Yes, exactly. So what I like to do, I like to use structural codes for exploring designs and
Yeah.
exploring the behavior of sections, and I think Jupyter Notebooks is a really good tool for doing that because you can go back and forth between cells and rerun thing and edit stuff. So in order to do that in VS Code, you need to first of all you need to have a Python environment where you have structural codes installed, and you need to have a Jupyter kernel running. Let's leave a couple of links in the show notes, perhaps, to
Yeah.
these
Yeah.
libraries. It's also a good thing to have NB format installed, which will allow you to show plots inline, for example. And in order to operate on this inside VS Code, you should also have the Jupyter extension and the Python extension. One thing that's not strictly necessary is to use the rough extension for formatting the code. I tend to always have that running to kind of help me format my code nicely. I will link to that also.
That's probably something that becomes, very important when you're actually trying to publish a tool like this.
Yeah,
But
sure.
it probably overkill for just somebody that's regularly trying to use this code. But I
Yep,
think it does instill good practice.
that's a good point. So it's not strictly necessary, but nice to have.
Okay.
So we can now recognize here the code blocks from our online documentation.
Yep.
And we can simply click run all, and then this is live coding. So let's keep our fingers crossed. We have green lights here. Let me
Yep.
first show one thing that's really nice when you work inside a Jupyter notebook in VS Code or in any platform. When you have a geometry object, this can be automatically displayed in your notebook. So remember that the geometry object here, which is
Hmm.
a compound geometry,
Yep.
if we make sure that that's a return from a cell, you can immediately see
Nice.
it. This is, to me, this is magic. Some magic that's included inside a Jupyter notebook. It's good to just have this kind of displayed so that you see what's happening.
Yep. Yep.
Next, we can do, well, let's have a look at some alternative ways to model this. So
Just as a general point, Morten,
sure.
like almost whenever I'm doing any sort of complicated design work, I'm constantly trying to find visual representations of what I'm doing, because
Hmm.
when you're in the midst of something, I can't remember what I did 5 minutes ago, and I need to kind of keep checking to make sure that I didn't forget the reinforcement. I don't have it's a 20-meter deep section. No, I wanted a 2-meter deep section, all that kind of stuff.
Yeah. Yeah, in order to have some more visualization there, let's import matplotlib and also plot the response. So in this environment that we're running now, I have also pip installed matplotlib. So we can do import matplotlib.pyplot as plt, for example. So we can go back to the bottom here, and we see this call to calculate moment curvature returned a moment curvature result object.
Hmm.
So let's now have a look at what this actually produced. So I'll create a figure and an axis object. And on the axis object, I will plot the curvature and the moment. So the moment curvature object here contains the curvature and the moment. Due to our sign convention, we should plot the negative of those. So let's now see what these looks like. So here you see a quite linear branch up to yielding of the reinforcement.
Yep.
And then you have kind of this post-yielding curve until you reach final compressive failure in the concrete.
So this is a great example of what you'd mentioned earlier on, where you said that once you finalize your geometry section,
Mm.
then you're actually wrapping it in all of these various hidden functions that are your constituent laws or constitutive laws that allow you to create this exact plot.
Exactly. Yeah.
And so the functions that were used to create this plot, do users need to, like, how do they know what's available? Like I guess if you hover over your geometry variable, it shows what methods are available to them.
Yeah, let's have a look at that. So we had the section. That's what wraps the geometry and exposes the methods of the section calculator. So if we do dot section calculator and then press a dot, now
Nice.
we see the methods that are available to us. So we could do a calculate bending strength just to see what that returns. Let's see now if I can scroll here. So it says the bending strength is, let's try 178.5. Let's see if we can recognize that from the graph here. Yeah, so that would be the point up here in the graph. So 178.5.
Cool. And so I noticed that as you hovered on each one of the, so you've got like all of these methods available to you, and you've also got detailed documentation on each one of these methods so that people can see what type of inputs are required. There's a doc string tied to each one of these to figure out what they are. And it's important to remember, if you don't recognize what some of these terms are, it's because they're tied to the Eurocode too.
Yeah, it might be.
And there's many different, like very, very similar, but just worded slightly different in other design codes, such as the US or the Canadian design codes, which I'm more familiar with. Okay, that's awesome, Morten. Carry on.
Yeah, so let's now see if we can explore some other classes here. Well, we did this surface geometry. So we used the surface geometry to model the geometry.
Mm-hmm.
We can also use the rectangular geometry class to speed up the modeling a bit. So remember that we actually created a polygon, and in order to kind of shuffle these coordinates right, you need to spend some time thinking.
Mm-hmm.
So instead, we could do a geometry equals a rectangular geometry. So create an instance of the rectangular geometry class. So here we simply specify a width and the height and the material. So let's now see what happens if we do like that. I will click save, and let's see if it runs all of it.
So where did you define your width and your height? Are they way back up at the beginning? Oh,
Good
yeah, right
question.
there.
Yeah, that
Cool.
was right here, but it was barely visible. As you ask the question, well, we also we are using millimeters by default in
Yep.
our library. I guess we can get back to units later in the conversation, but
Yeah.
by default
we
we're
don't
talking about millimeters here.
we don't want to derail this entire conversation just yet.
Let's skip. Let's save that for the end.
Yeah.
But yeah, so my point here was that we can use these wrapper classes for creating geometries a bit more easily.
And so, okay, so that's a quick way of creating a rectangular cross section. And then when you go back down to when you're defining where your reinforcement sits,
Yeah.
So you're entering in. Oh yeah, there you go. You got your cover and you got your diameter, and then how is it defined? Sort of your horizontal position of the bar. That's? Oh yeah, I see here. Right. Okay, gotcha.
So I kind of skip the names of the keyboard arguments here, but these two, or this function call add reinforcement, it
Gotcha.
adds a point to a given coordinate. But
Yeah.
we can
Yeah.
also simplify that. So let's do a I will do a new import on the top here. So we will do a add a reinforcement line. You could probably guess what it does. So it
Mm-hmm.
adds reinforcement along a line. So we could do a geometry equals add reinforcement line.
Mm-hmm.
So in this function, we should specify a geometry object. We should specify a starting coordinate and a final coordinate. So those will be the coordinates of those two reinforcement bars that we already provided. So I'll simply just copy those. And we should provide a diameter of the bar and a
Mm-hmm.
material. So diameter, we can do like this, and we can do reinforcement, which was the material. And then finally, we should either provide a number of bars to add
Mm-hmm.
along this line or a center distance.
Mm-hmm.
So let's now do a n equals 2, for example,
Mm-hmm.
or we could even do n bars equals 2, and then we have it defined up here. Let's now skip these two, comment them out. We can rerun everything. Let's skip down to the geometry plot and see. This looks
Yes.
quite similar to what we already had, but it's
Yeah.
a bit simpler, especially if we need to, say, increase the number of bars, say increase it to 4 bars,
Yep.
then
Nice.
we should have 4 bars. Okay, this is quite heavily reinforced, or they're quite close to each other, so
Sure.
perhaps not the best design, but
And would something like that is for Eurocode in particular, would you get some sort of a error code to say you've tried to place 4 bars in this relatively narrow section, the spacing is inadequate, or some sort of warning code like that?
yeah, that's a good question. And I mean, that could perhaps be a good feature, but we have not
But
implemented that.
and there's no end to things like that. So you just need to be very careful about what kinds of warning signs you get into, because
Mm.
everything grows legs so quickly.
Yeah, it does. But I mean,
Um,
I guess it's an interesting one though, and I think it could belong, or it could perhaps more belong in the front end built on top of this, because you can always kind of derive the center distances from the input and then
yeah.
check the center distance based on features in the kind of the core of the structural codes library. So yeah, it's a good one.
Um, okay, so is there any other classes that you want to cover here before we kind of zoom out and look at the overall architecture of structural codes?
Yeah, well, not really. Well, we could perhaps just browse through the available methods on the section calculator. So, so just to kind of have an overview over what's available. Well,
Mm,
we already covered the bending strength, but you also have the
mm-hmm.
limit axial load. So that would be the maximum tensile and the compressive axial load you can put on it. You also have interaction domains. So both pure biaxial bending for a
Mm-hmm.
given axial force. You have the interaction domain for one axial force and one moment, and also kind of a three-dimensional space where you have biaxial bending and axial force. We also have the calculate strain profile based on a set of axial force and biaxial moment,
Mm-hmm.
which is, I mean, that's really useful for calculating the response of the section to a given load. Typically, that could be input to a crack weight calculation, for example.
Yeah.
And you have the inverse of that, so integrating the strain profile in order to get the axial force and biaxial bending based on strain and two curvatures.
So there's a lot of really useful methods in here that can take your output, like if, whatever structural analysis tool that you're using, whether it's, you know, simplified hand calculations or advanced finite element models, you can take those outputs and then use the methods in here to either to double check your results or to ensure compliance with whatever design code you're using. And in your case, it's Eurocode 2.
Mm. Yeah, I think that's a typical workflow that you described there. So one workflow could perhaps be that you're actually using this as a post-processing tool.
Yeah.
Um, and I've seen examples of this actually from my colleagues. One colleague who used structural codes inside of Grasshopper in order
Hmm.
to post-process and check the capacity based on results from FEM design, so finite element analysis results. But I've also
That's
seen,
how I've been using it, Morten,
right.
personally, is I'm doing my analyses in either SAP or Pinite or Strand 7. And then when I have demands, I'm kind of running through some custom classes that I've made for ACI 318
Mhm.
in the, as you've just described.
Yeah, I just stopped sharing. Figured that's better. And I mean, the second workflow that we could touch upon here is perhaps another interesting one, because I've also seen that some people find the library quite useful for iterating of a design. So say you have a geometry that's highly irregular, then it becomes a mess to model it often in usual commercial software. So I've seen that people kind of play around with dimensions and reinforcement layouts in order to find something that actually works. And then they put this into a commercial tool in order to get access to, for example, report generating, so that the final design is inside the commercial available tool that everyone trusts.
You know, it's difficult to, I guess, just broadly speaking, my experience with using these type of libraries is initially when I looked at structural codes, I was, you know, it's intimidating because of how much work you guys have already done.
Mm.
And you look at it and you're like, whoa, there's so much stuff here. But when you understand how it works and you understand the freedom that you have to use the building blocks however you want, if you want to change something to suit what you need to do, go ahead and change it. There's complete freedom. And
Mm.
that is incredibly useful for engineers because you're really, in my mind, you're only constrained by your own imagination of how to solve a problem. And that's what I love about these types of tools. Um, so for anybody out there that felt like, you know, as Morten was running through those examples, it's a lot to take in just initially because there's, you know, there's so much stuff that you can do, but it really is worth taking the time to just investigate, look around, read through the different folders, how it's structured. So maybe let's talk about that, Martin. So
Yep.
you gave us a kind of a snapshot of one particular section of structural codes, but when we
Yeah.
zoom out, give us an overview of what it is and how it's built.
Yeah. Good idea. I mean, from the very beginning, we wanted to kind of create a structure to the library. So just as you say, to help the user in browsing through the library. So we initially we kind of visualized or at least three levels in the hierarchy. So in the core layer or the bottom layer, we have the design code equations. So there we have function implementations of all or quite many design code equations. And one goal there is that the function should have the same signature. And then, I mean, you should have the same parameters entering the function as in the design code
Yeah,
so that it's one to one with the code.
yeah, yeah.
Um, I think the usefulness of that is that you get what you expect. So you immediately see what to put in there.
Yeah, no
The
interpretation. It's like for like. There's no arguments about what is this variable, what does that mean. It's like it's called this in the code, it's called this in structural codes.
Exactly. And one possible or potential drawback of it is that you get a whole lot of functions. So for every little additional equation, you get one function. I got a funny comment on LinkedIn the other day where this guy discovered a function that simply just returned 1, so 1.0. But I mean, that's the result of having such a structure of it. At least the function said what this 1.0 meant.
Yeah, yeah,
Yep.
where it came from.
Yep.
And that's an entirely different conversation. But I think that's what you have to do. You have to replicate like the code is full of functions. So
Mm,
like the actual design code is full of functions. So you got to replicate those functions programmatically.
exactly. Exactly.
Um, okay, so can you share your screen to show the the architecture of it, just how it's laid out?
Yeah. Let's see. Let's see now. We can go back to the documentation. So, and we can go to the API reference, and we actually have a separate block here related to library structure.
Nice.
So on the first level, as we just discussed, we have the code equations. On the second level, so this is kind of where you use things or you start using things from the base layer. This
Yeah.
is where we have the materials and the constitutive laws. So the material classes, they are kind of collections of material properties and attributes related to the materials. And on the top level, at least for the moment, we have the sections and the geometries. So this is where we tie it all together and we do the calculations. We can also have a look at our GitHub repo. You will see the
Yes.
exact same thing here.
Yes.
So if you browse the code, you can see that we have a separate folder for codes. Inside that folder, you have one folder for each of the codes that we've implemented so far. So
Yes.
one for Eurocode 2 2004, and also for the Eurocode that we're currently working on. So this is not a governing code, but it's a code that we're developing for the moment.
Yep.
We have the FIB model code 2010 and the new model code 2020. Furthermore, you see materials down here and constitutive laws. You see geometry over here, and you see sections over here. And for those who are seeing the code now, you see that there's many underscores and double underscores, so dunder, inside these file names. So
Hmm.
this is our way of saying that or differentiating between what's kind of private and what's the public API. So you're basically not meant to enter this module from outside, but we expose stuff from that module outside of it.
So when you go back to you're defining your geometries and defining your reinforcement, and you want to use some section proper you want to do some section properties checks, etc.
Yeah,
You're calling the methods from all of these additional dunder files, and you're getting the various documentations and everything that you need to use those methods.
yeah,
But you don't need to go in there and start messing around with stuff unless you actually want to add or refine additional methods. And to do that, you would have to uh, create a branch of the structural codes repository, which is what I've done. And if you go back briefly,
mhm.
Morten,
Yeah,
to
sure.
the GitHub folder structure,
Yep.
um, so in the structural codes folder there,
Mhm.
so in here where Morten has the actual different design codes, I've been working on one for ACI 318-19, which would fit into this folder.
Mm.
But the way that Morten and the rest of the contributors have created the architecture. It's such that the code specific functions are defined in this particular folder.
Mm,
And then obviously the geometry, the materials, the constitutive laws, etc. Those are common to all structural codes around the world. And maybe some of them might interpret certain aspects differently than others. And that will kind of have to be refined as I get through the ACI 318 stuff. But
mm,
broadly speaking, the big difference that I found between Eurocode and ACI is that there's more variability in the different types of partial factors that you can use in Eurocode. You've got a broader range of specific safety factors or material factors that give you a bit more flexibility to kind of create the most efficient design for a specific purpose. Whereas the US based codes are there's less variability and we're a little bit more rigid in terms of the material factors and the safety factors. That's
mm.
probably the biggest difference that I found. But again, that's not really relevant to how you've structured the library. It's just a kind of an observation. And I think the same
Mm.
goes for the Australian and New Zealand structural codes. They're all kind of derivative of one another, I would say.
Yeah, I think those are good observations. And I mean, there's also this difference in where you apply the partial factors, isn't it? So in at least Eurocode and the FIB model code, we tend to have the partial factors on the material properties. So that's what entering in our section calculations inside structural codes. So you have kind of the design constitutive law that enters into the calculations. However, I think it's like that in the ACI code that you're kind of entering more characteristic or representative values, and then you
Yeah.
apply the material or the partial factor on the response, so on the moment capacity, if I'm not
Yes.
mistaken.
Yes. Yeah, and you have different factors for different situations. And
Mm,
so the constitutive laws, if we go into that folder just for a moment, and
yeah,
this is the
sure.
one I don't want to scare anybody, but there is a lot of really good stuff in here. And, as I went through this, I was like, holy smokes, this is going to take me a while to digest because there is a lot of very good theoretical functions in here that can give you a very deep understanding of what's happening with your cross section as long as you've got the right inputs. So, what was the most challenging part of this to create, Morten?
I think the most challenging, or I mean, the most challenging part was to kind of stitch all the section API together.
Yeah, I bet.
So from the very beginning, we knew that we wanted to have kind of a modular approach. So being able to swap objects in and out, and we knew that we wanted to have some really flexible calculation tool that allowed us to model an arbitrary geometry with arbitrary reinforcement layout. And you can kind of quite easily think of methods that would first kind of, for example, triangulate the geometry. So split it into small parts and do
Mm,
separate calculations for each part,
yeah.
and then kind of do a sum overall to get the stress resultants. But
S-
having such functions might become huge and hard to maintain. Uh,
That's a tightrope that you're just walking all the
yeah,
time with this tool. Um,
exactly.
I had a question there, and now it's gone out of I just canceled it out of my head. Oh yeah, it was. So you've mentioned we've mentioned functions and we've mentioned objects and we've mentioned methods and we've mentioned classes.
Yeah,
Would you mind just using structural codes as an example, just to explain to somebody in a structural engineering context, like what each one of those things are?
yeah. That's a That's a really good suggestion. Well, inside the codes folder here, you will find different modules. So each of these files, that's a module. For example, concrete creep and shrinkage.
Yep.
And inside each of these modules, we have defined functions. So a function in Python, that's something that you define with a def keyword, the name of the function, and then the arguments and keyword arguments, so the parameters that enter into the function. So inside the function body, you do some calculations. You can do simple plus and minus. You can use trigonometric functions. You can do array operations, if, else, blocks, loops, etc.
Hmm.
And then you return something.
So
So the
any
basic
type
structure
of,
is some. Sorry, go ahead.
I was just going to say, it's any type of predefined calculation
Exactly.
where the user just puts in the input. It's like a predefined recipe for a calculation. The user just puts in his inputs, runs it, and then you get your result.
Yep. Exactly. So you enter an amount of ingredients, and then to get the final results out. So if we head over to classes, we can have a look at, for example, let's have a look at the material classes.
Yeah.
And we can have a look at the concrete for Eurocode 2 2004, for example. So a class, that's kind of a blueprint for something. So a class could be then a person, for example. I guess that's the school example. That's a blueprint for a person, and it should have attributes. So perhaps a name, an age, etc. In structural codes, you can have a class, so a blueprint for a concrete from Eurocode 2. And this has attributes. So for example, the cylinder compressive strength,
Hmm.
the Young's modulus,
Hmm.
and many other attributes. So those are properties of the class or properties of the object that you create based on this class.
So if I define a concrete for ACI 318-19, I will have, maybe they'll be slightly different, but maybe I have 6, 7, 8 different very specific parameters of that concrete. I enter them in, and then that particular type of concrete, let's say I'm dealing with concrete in a highly corrosive environment that has maybe a slightly different mix design, slightly different properties. I would define that particular type of concrete as a class. I would enter in all of these various attributes, and
Yep.
then as I do my calculations, I can call that, I can I can reference that particular type of concrete, and all those attributes will be automatically tied to it, and that will carry through my calculations, right?
Exactly. That's a
Okay.
brilliant description of it.
Okay.
Now, yeah, but then as we enter into the class, we can also find the methods. So remember that we talked about functions. So a function inside a class, that's called a method of the class.
So a specific calculation that is tied directly to this type of Eurocode concrete.
Exactly.
Only available to the Eurocode concrete.
For example,
Right. Yes.
um, one nice thing that we do here is that we create our concretes as subclasses of a base concrete class. We can have a look at that also. So the base concrete class is actually a subclass of the base material class. So
This
let's
is like a fractal wormhole.
yeah, it kind of is. But I mean, the reason why I'm bringing this up is that I think this could be a good place to start experimenting with with the structural codes.
Yeah.
So one thing that you will see is that in the base class, For example, you have defined a property which is the constitutive law. So this base class, that's where we define the interface. So here we defined the methods that are necessary for a class to behave as a material class in structural codes. And why are we doing that? Well, when we do this, we can quite easily swap the material with another material, and then the geometry and furthermore the section will treat it as just another material, and it will ask this material for relevant properties. For example, then the constitutive law, which could, for example, be an elastic plastic law, which also has a predefined interface. So then the section will know that, well, this is a material. I can get the constitutive law from the material. And from the constitutive law, I know that I can use the methods get stress, get tangent, get secant, for example, or get ultimate strains, just to name a few.
This type of abstraction is extremely unusual for most practicing engineers, and even just to think about how to lay this out and what the best way is to structure it all has been making my head spin. And as you're just kind of walking through, how and why each of these steps are important, it really helps you understand the not the workflow, but the process of, programmatically, how do you walk through this process. It's almost like understanding how regular commercial software works. So I find it really beneficial for you to walk through this stuff. And for people listening, if it feels like a lot, that's totally normal, because it is. It is a lot. But being able to understand these kind of fundamental relationships between constitutive laws and your code, your local codes that you use, is a huge benefit to your overall understanding of structural engineering. Sorry, Morten, go ahead.
No, that's a good comment. I'm glad that you see it like this. I mean, I think the next step in kind of the exploring here is perhaps to see how you as a user can do your own stuff based on this.
Yeah.
And we can go back to our Visual Studio Codes window. We can explore it a bit further. So as I mentioned, we have the section. That's kind of the ultimate level. Inside the section, you refer to a geometry, and the geometry refers to a material. And the material, that's kind of a wrapper for basic ingredients from the design code. So a starting point for adapting this to any of your special needs would be to, for example, create a class. So my special concrete, for example.
Yep.
We should do a from structural codes dot materials dot concrete import. We could do a concrete Eurocode to 2004, for example. Then we can subclass this one. So concrete EC2 2004. Let's just leave it like that. Now we can use this special concrete, which is concrete EC2 2004 based in our calculations. We could also do a def init of this one. And in here, we could, for example, do so we call the constructor of the base class.
So what's happening here?
So here we make sure that we actually do all we call the necessary parts of the code in order to have this special objects behave as the concrete EC2 2004.
Mm-hmm.
But in addition to this, we really want to change the default constitutive law, for example. So let's now do a from structuralcodes.materials.constitutive laws import elastic, for example.
Yep.
So let's now say that our really special concrete, it takes Young's modulus as an argument.
Yep.
Now we make sure that we set the constitutive law as an elastic material with a Young's modulus equals to our Young's modulus. So we can now do a concrete equals my special concrete with a Young's modulus of, say, 30,000
Mm-hmm.
megapascal.
Yep.
And we should pass another argument as well. So let's just leave this dummy for now. Now this concrete of ours, it will have a constitutive law attribute, which is elastic.
Okay.
So if we pass this one to our section or to our geometry and our section object,
Yep.
all our calculations will be based on an elastic concrete.
So if we take ourselves back to the plot that you showed of the stress strain diagram, where you've got that yield point, in this case, that the plot would just go exponentially off into the distance at a slope, and there would be no yield.
Yeah, probably. Let's see what happens. I did not test this.
Here we go, folks. There we go. Who would have thought? It worked.
Yeah, it did.
Okay, look, Morten, we're running out of time here, and I think what do you want to close off on this, because I think we've really only scratched the surface of how deep this library is. There's so much stuff. It can do so many different things, and the general goal here today was to kind of show people an overview and to encourage people to investigate and to dig in and try and figure out what's going on, because there's a lot there. And hopefully we can talk again in the future when
I would love to.
and maybe go in more detail on certain aspects of it. But is there anything that you want to close off with, or any kind of messages that you want to send out there to the community, or to people that are interested in contributing to a project like Structural Codes, and not even just contributing to it, but maybe just using it? Like my plan is to add the stuff that I use for ACI 318. Obviously, everything takes time, but that's what I'm kind of working on the side. But what do you have to say about any of that?
Well, I think first point is try to get involved. Start experimenting. If you find a bug, I would love to hear about it so we can fix it. If you see the need for more features or other codes, please reach out. And as you already did, you asked the question in an issue on GitHub, and that led to this conversation. So I really appreciate that. And then while exploring, try to see whether there are options for adapting it to your needs. So I hope that I at least succeeded slightly in showing off the modularity of the library.
Yeah.
And through this modularity, you should be able to kind of swap parts of it. So define your own material, swap it with another one. You could even subclass the section calculator in order to define other methods for calculating other stuff. And
No,
as you mentioned, we kind of just briefly touched upon the content of or all these functions that are present in the design code layer here. So we have functions for share design, we have creep and shrinkage, we have crack width calculations, etc. These are not directly tied to the sections because there's not an easy tie into there, but some connections will come in the future, I think. But yeah, I think you will have the basic ingredients for building say, at least a notebook that could be used as your go-to design tool.
Yeah, I agree, and I think even for me to just the exercise of trying to understand how everything is put together, how it works, I can feel myself developing a deeper understanding of just capacity-based design as I kind of try to explore how it works, and then it even leads to me being able to use commercial software better because I'm asking those questions like, wait a minute, how is like why is it using this particular variable, or what just happened?
Mm.
A comment I had posted about this a while back on Reddit, and I asked people what their interest was in this or if they had any suggestions, and I got a bunch of DMs related to this,
Mm.
and a lot of them were like suggestions of, oh, you should add this, and a lot of it was analysis based stuff. And
Mm.
I think it's really important to reiterate that once again, that structural codes is not intended to be an analysis suite, like a finite and element analysis suite. That's not what the goal is here. This is to connect your results with your structural design code that you're trying to work on. And in Morten's case, he demonstrated Eurocode 2 today. So if you're a Eurocode user, it's all here on a plate for you. A fantastic library. You have to investigate it. And for the rest of us, we just have to think about how we can use this modular architecture to support our design codes. And so if there's people out there interested in contributing to Australian, New Zealand, Indian, I'm working on the US, but the more help, the better.
Mm.
Canadian, like, get in touch. You can reach out to Morten. He's maintaining the library. I've branched my own version of structural codes, and I'm using it here at work. And when I'm ready, I'll start to submit stuff for review. And it's going to start off very, very simple. Just basic flexural checks, basic shear checks, basic axial capacity checks. Nothing fancy until we start to build some momentum.
Cool.
So Morten, thank you very much. A really, really interesting chat today. And also, I
Thank you.
think the first time that we've done some live coding on the podcast where we kind of walk through some stuff. And I found it very engaging myself. I'm already interested in this stuff anyway, so I guess we'll find out soon if that's not the case globally.
Good. Glad to hear this, James. Really appreciate it to be part of this. So thank you
Awesome.
for inviting me.
Awesome. For everybody out there, links are all down below. Thank you very much for listening, and I'll catch you guys in the next one. All the best. And a happy new year, happy 2025 to everybody.